So for this lesson, we're going to extend our thinking about parallel lines and then also start talking about perpendicular lines. And perpendicular lines are lines that they cross, but they particularly cross at 90-degree angles, okay, like that. But anyhow, first we're going to deal with these parallel lines, and this is what this one says. If two lines are parallel to the same line, then they're parallel to each other. If A is parallel to B and C is parallel to B, then A and C are both parallel to each other. It's very much an extension of the idea of the transitive property, okay? So this theorem deals with perpendicular lines. In a plane, we're on a flat surface. All three of these lines are on the same plane. If two lines are perpendicular to the same line, then they're parallel to each other. If M is perpendicular to T, as you can see it is, and N is also perpendicular to T, then they're going to be parallel to each other, okay? And it says, notice that Theorem 3.9 includes the phrase in a plane, because in exercise 17, you'll consider why that's necessary. So here's proof of this theorem that's above. In a plane, R is perpendicular to T, this symbology right there you can see, and S is perpendicular to T. Okay, since they're perpendicular, and we're trying to prove that R is parallel to S. Since they're perpendicular, that means that we have a 90-degree angle here. We have a 90-degree angle here, okay? So it says angles 1 and 2 are right angles by the definition of perpendicular, and so angle 1 is congruent to angle 2, and since corresponding angles are congruent, you can see that they're corresponding angles. By the converse of the corresponding angles theorem, these two lines are parallel. All right, so this is just a word problem applying the ideas that we know. A carpenter plans to install molding on the sides and top of a doorway. Okay, the carpenter cuts the ends of the top piece at a 45-degree angle and one end of each side piece at a 45-degree angle. Will the side pieces of the modeling be parallel? Will these two side pieces be parallel? Well, we know that the angles are 45 degrees, and we need to determine whether they're parallel. So what we need to do is fit them together mentally, or and then what do we get as an angle here? Remember, the angle addition postulate says this is 45 and 45. So sum together 45 and 45. What's that going to sum together to be? And as you should know, they will sum to be 90. And since they sum to 90, that means that these are perpendicular. Okay, 90 here means this is perpendicular with this. Side pieces are both perpendicular with the top. And remember, if two lines are perpendicular to some other line, they're parallel to each other. Okay. Yes, the sides are parallel. When the pieces fit together, they form 45 plus 45 or 90-degree angles. So each side is perpendicular to the top. If two lines, in this case the sides are perpendicular to the same line, the top, they're parallel to each other. Yep. Okay, what about this one? Can you assemble the pieces at the right to form a picture frame with opposite sides parallel? Explain. So the two theorems that we were just dealing with showed you how you could conclude that the lines were parallel. But this one, the perpendicular transversal theorem, shows how you can conclude that lines are perpendicular, okay? So in a plane, if a line is perpendicular to one of two parallel lines, now we know that the lines are parallel, okay, which then of course we're going to know that corresponding angles are congruent, right? Since the lines are parallel, and it is perpendicular to one of them, that's a 90-degree angle, then this will be as well. And so therefore, the lines are perpendicular here. Yep, N is perpendicular to M. For the reason that when the lines are parallel, corresponding angles are congruent, and if this one is 90, this one is 92. And if it's 90, that means it's perpendicular. Okay, so the perpendicular transversal theorem states that the lines must be in a plane. Here's a box where you see these different planes, okay? Diagram at the right shows why. In a rectangular solid, AC, right here, and BD are parallel. Now, EC is perpendicular to AC, but it's not perpendicular to BD, and they're in fact skew, okay? They're not on the same plane, they are skew. So you can be perpendicular to this one and not be perpendicular to this one if they're not all on the same plane, and that's why that's required. Okay, so here you're proving some relationship between two lines. In this case, they want us to prove that C right here is perpendicular to A, and it's not extended all the way out and you don't see any marks. But we do know these things, and what's given is also marked over here. C is perpendicular to B, that's right here. B is perpendicular to D right here, and D is perpendicular to A. So we're trying to prove that if you extended this line C out to intersect with A, they would be perpendicular. Okay. Now, note this. Oops. Thank you for your patience there. Lines C and D are both perpendicular to B, and remember, if two lines are perpendicular to some other lines, they're parallel to each other, right? So here it says C and D are parallel because two lines that are perpendicular to the same line, in this case B, are parallel. So now we know C and D are parallel. And we've also been given that D is perpendicular to A. So therefore, C must be perpendicular to A as well, because a line that's perpendicular to one of two parallel lines, and we determined that these are parallel because they're both perpendicular to B. If some line is perpendicular to one of two parallel lines, it's perpendicular to the other one. And since A is perpendicular to D, it's also perpendicular to C because we've determined they're parallel. That is the perpendicular transversal theorem. Okay. See what you can do with this one. Can you also conclude that A is parallel to B and explain it? All right, there you go. That's the long and short of it. Try these lesson check problems, and if you feel like that was quick and you got it all, then prove it.